This video discusses shapes of distributions. When describing a distribution, we want to make sure that we always talk about three things: the shape, the center, and the spread. Does the histogram have a single central lump or several separated lumps? Is the histogram symmetric? Do any unusual features stick out? We'll look at some examples of these. Now here's some common distribution shapes. We have the bell shape. This is the triangular shape. Uniform, what's called the reverse J. The J shape. Sometimes this is known as an exponential growth. This would be a exponential decay. Skewed right, skewed left, bimodal, multimodal. And we'll discuss these more in this video. But the common four types that we're going to discuss in Stats 1 is bell shape, uniform, skewed right, and skewed left. But we'll also discuss bimodal and multimodal. Does the histogram have a single central hump or several separated humps? The humps in a histogram are called modes. A histogram with one peak is dubbed unimodal. Histogram with two peaks are bimodal, and histogram with three or more peaks are called multimodal. We'll look at some examples. In this case, this histogram, this is clearly bimodal. Go to the student survey data. This is the variable height, and if we look closely here, this is bimodal. Here's a peak and here's a peak, and if we think about it, this should make sense because this is men and women grouped together, and we know that men on average, this peak is taller or more to the right than female heights. And we can also see that the frequency, there's more women taking the survey than men. If the histogram does not appear to have any humps or modes, then we say that the distribution is what we call uniform, where approximately each band has the same frequency. Here's an example of using the data from the student survey. This is the random number variable, and we expected that the random numbers to be uniform. If you remember the question asked pick a number between 1 and 10, and as we can see, most people pick 7. So theoretically, we expected this to be random, where each digit had the same chance of being picked, but that is not the case. Most people pick the number 7. Is the distribution symmetric? If it is symmetric, then roughly along the peak, the left-hand side of the peak is approximately equal to the right-hand side. So the shapes of each of these bands to the right of the peak should be about the same, or approximately the same, to the left. It's the mirror image, so if we fold this over to this, we expect them to be about the same. Now this is the height, but this is separated for just females, and this would be approximately symmetric. We'd even probably say that this is bell shape. Let's look for the males. So we can see that the males have a different center, and this distribution is roughly bell shape also, and symmetric. The thinner ends of a distribution are what we call the tails. Now if one tail stretches out further than the other, then we say the distribution is skewed. Now we have two types of skewed, skewed left and skewed right. This is an example of what we call skewed left. If we find the peak and we draw a line out here, this would be the left tail, this would be the right tail. So this would be an example of skewed left. This would be an example of skewed right. This right tail is longer than this left tail. Here's an example of using the student survey data. Age, clearly this is skewed right. The right tail is a lot longer than the left tail. Now if we separate this variable by gender, male and female, let's see if it changes the shape. Here's female ages, there's males. Both are skewed right. It did not change the distribution when we separated by gender. The next thing we want to look at is there anything unusual about the histogram, about the distribution? Are there any what we call possible outliers? And that means values that are away from the rest of the body of the distribution. And this can be identified by if there's any large gaps. So in this case there is a possible outlier to the left. A histogram cannot identify outliers, only a box plot. And we'll talk about box plots later. Here's an example of a distribution. Again, this is skewed, but here we have possible outliers to the right. This is for the variable commute time. How long does it take you to get to Cincinnati State from home? So these are very large values to the right. Here's the same data set, but this time instead of a histogram, it's a dot plot. And again, we can see that there are possible outliers to the right. A dot plot only shows possible outliers. A box plot is the only graph that will tell us if a value is an outlier. Our last example is the variable woebegone. So there's something called the woebegone effect, and this is the question: on a scale from 1 to 10, how do you rate your intelligence? And we can see most people say 8, but we do have some possible outliers here. So we have about 200 people who say they're 10 out of 10. We have about a little bit more than 300 give themselves a 9. The largest peak here, a little bit under 700, maybe 780 people say they're an 8. 7 would be about 500. We have about 150 for 6, and for 5 we have about 100. So there is something called the woebegone effect, and it simply means that people, when you ask them how good they can drive, or you ask them about their intelligence, usually they'll almost always say they're above average. So in this case we have the majority of the people being way above average. Thanks for watching.